Atomic radius. Back to that. Back to radius. So, please stop talking. Pay attention. We're moving on, and I'm going to go quickly. So, here you go. All right. So, you got that it's the distance here. Short little video. We're just going to do the one. I'm going to skip the other because we're running out of time here. But, take a look.
At room temperature, the halogen element chlorine exists in the gas phase. Gas phase molecules are relatively far apart since gases have low densities. Molecules move in straight lines until they collide with container walls or other molecules. The diatomic chlorine molecule can be used to estimate the atomic radius of chlorine atoms. The distance between nuclear centers in chlorine is 199 picometers, so the atom radius is estimated to be 100 picometers.
Okay, picometers, yes, 10 to the minus 12. Very small. You realize that's very, very tiny. Okay, so keep that in mind as we're moving on here now, looking at our trends. In general, as you go from left to right, you're going to decrease. That's due to effective nuclear charge, because you're really adding more protons at a faster rate than you are having electrons be repulsive to one another. Okay? In general, atomic radius increases going down a group. We know that because we're increasing our principal energy levels, our quantum levels, that n value keeps growing. You're adding more core electrons. You're getting wider in general due to that fact. Okay? So keep that in mind about atomic radius. Now, we do have a few examples in here, although I didn't put them in your note sheet, but hopefully you can catch on. I like to think of atomic radius. I like to think of the trends going in the value going in the same direction. So this is how I look at atomic radius. I say it increases left and down. Most of the other ones increase if you go up and to the right. Okay? So I like my trends to be going the same direction in the way I think about them. So instead of going, left to right is decrease and then down is increase, I say left and down is increasing. So you might want to think about it that way. Okay? So atomic radius, obviously effective nuclear charge, that's a key word that you would use in a justification here if you had to do this in a free response. Okay? Keep that in mind. So some pictures of the radii you can see up here. As you go to the right, their circles keep getting smaller. Helium, technically, I guess, would be the very smallest on the table, whereas francium would be the largest. If you're following the trends, of course. This one doesn't really have a lot of exceptions to it, so which should be the larger atom and why? Sodium, yes. Why is it sodium? Okay, yes. Saying left, though, on a free response is not going to get you a point. What would you need to say? Yeah. The chlorine, yes, has more effective nuclear charge. It has more protons, and it's pulling in those electrons closer. Something like that along those lines would be good for a justification there. Okay? Which should be the larger atom, lithium or cesium? Cesium. Cesium's in the same group, so it's kind of easy to tell there. So as you go down, you're adding more energy levels. You're going into the sixth energy level, so you have a lot more core electrons and you're a lot wider. So yes, cesium. Now, this one's a little tricky. Think about it. Although it's not on your paper, but think about it. Which is larger, the hydrogen 1s orbital or the lithium 1s orbital? Why would it be hydrogen? Yes, you have less protons, and you have, so it's going to spread out and be a little bit further away. Whereas lithium has 3, so it's going to pull that 1s in a little bit closer. But do realize lithium is still larger in general as an atom. It's larger than hydrogen. It's just that 1s is a little bit smaller due to the fact that it has 3 protons rather than 1. Okay? Which is lower in energy? Why would it be lithium? Why is it not hydrogen? What did we learn about in our photoelectron spectroscopy? Closer you are to the nucleus, the lower your energy for the electron. So if you're closer in, remember 1s is the lowest energy level. So if it's closer in, lithium's is closer in, we just determined that in the first statement or the first question. So then lithium would have to be lower because it's closer to the nucleus. Now the binding energy from the nucleus is higher. We know that from our photoelectron spectroscopy as well. All right, so ionic size. Now looking at ions. Okay, ions depends on their nuclear charge, the number of electrons, and the orbitals in which the electrons reside. However, our general trends are going to be that cations, they lose electrons, they generally become smaller than their parent atom. Okay? So their outermost valence electrons are the ones being removed, so they do generally shrink. Okay? And here on the picture you can see, like here's a lithium right here in comparison to the lithium ion. So it definitely shrinks. And if that is true about our cations, what do you think will happen to our anions? They do get bigger, okay? And they're because you're adding in electrons, you have more electron repulsion, so your cloud is going to be a little bit bigger, okay? So as you see here, here would be a regular neutral sulfur. Here is sulfide, definitely a lot bigger, okay? And you generally will increase in size as you go down a column, and that's also the same with the regular trend with atomic radius, because you're just generally increasing your energy level. So like in comparison, sodium's ion comparison to potassium's ion, obviously potassium's ion will be bigger. Okay, so as you go down a group, that's what we're looking at there. And in an isoelectronic series, ions will have the same number of electrons. Okay, we're going to go over this in detail in the next set of notes, so I'm not going to spend too much time on it right now. Ionic size decreases with increasing nuclear charge. Why? Because those protons pull them in closer and so forth. Okay, so we'll get into an example like this in the next set of notes. What does isoelectronic mean again? Same configurations, yes. Same number of electrons, same configurations. Good. Okay. Continuing on, here we go, yes. All right, exercise. Arrange the elements oxygen, fluorine, and sulfur according to increasing ionization energy and atomic radius. So what do you think about that? So, hopefully you got these down. And what did we decide for ionization energy?
SOF.
SOF?
SOF.
SOF, okay. Yes, that generally would follow the right trend there. Okay, atomic size? FOS, FOS. Let's see if you're right. Oh, very good. Okay. Luckily, there wasn't any exceptions in the ionization energy question there. So, good. All right, now, metallic character. Remembering that most of our periodic table is composed of metals, the majority. All this, to the left of the staircase, okay? Except for our two metalloids here, antimony and germanium. Lots of metals, very few nonmetals, and your metalloids there. But increasing metallic character as you go to the left, increasing metallic character as you go down a group. And lots of our, instead of having you write them down, I put the characteristics in here for you, remembering that metals are shiny and they have luster and nonmetals do not, and the metals are good conductors, whereas nonmetals are poor conductors. There are a few other here that you probably don't recall, like metal oxides that are ionic solids are basic, whereas the nonmetal oxides form acidic solutions. But the main thing here in determining the metallic character is that metals tend to form cations and nonmetals tend to form anions. And I gave you this chart to help you remember a lot of the more frequently used mom charges here. Do remember, like chromium 3 does have other, chromium has other charges, but the chromium 3 is the one that's predominant out of them, the one that appears the most. Okay, so giving you some ideas here too for that. And then of course we do need, I don't want anybody to miss a group name question on the test. That would be silly. We all know our major group names, right? Alkali metals, alkaline earth metals, transition, lanthanides, actinides, halogens, and noble gases, right?
They better know it. They don't.
Okay, you better know that for the AP test. That should be your easiest question. But kind of by that. Okay, so in this PowerPoint, though, if you'd like to review some of the major characteristics of each group, okay, you're welcome to do that. And then like here, this is just showing you pictures of metals. These aren't actually in your notes, but there are other slides here if you'd like to go through them. The metal oxides tend to be basic. Okay, nonmetals, poor conductors. Nonmetals form oxides that are acidic. Metalloids have properties of both. Some are shiny, some are good conductors of the electricity without all the heat and so forth. That's what we like in our electronic devices, of course. Okay. Group trends, so this is what I'm talking about. Like if you want to go back and look up some of the main characteristics of alkali metals, they're very reactive. They don't exist in nature by themselves, that kind of thing. I'm sure you remember from last year that they're soft and they react violently with water. Did everybody see that video with the big explosion as you went down the group? It got worse and more explosive. Okay, so famously exothermic in that respect. So if you want to go back through, as you see, alkaline earth metals are not as reactive. Their densities are a little bit higher. Okay, so forth. You can continue on if you'd like to look through the other sections, but I do want to point out one other quick thing that's very important about all of our chemicals, and you probably know this. This one is right here. How do I get up? Okay. The number and type of valence electrons primarily is what drives its chemistry. So the valence electrons go by the group, and that's the major characteristic that will determine its reactivity. Okay, so don't forget that that's really important for each group, and that's why they behave certain ways, okay? So keep that in mind. On the back of this packet is the instructions for Lewis dot drawings, and yes, you should practice a little bit over the break. Make sure you know how to do Lewis dot drawings again. I will do a few on Tuesday when we get back as we're doing the shapes, but if you need serious guidance in this respect, you might want to come see me, for additional help. Chucky?